Hello and welcome to another episode of Will and Connor's Particle Physics with Will and Connor.
I refuse to take part in this.
Right, what was that? Right,
That was...
today we are going to be doing a whole load of particle physics, trying to finish off the topic, and if we don't, you will know because of the length of this video. I do apologise. It's all Connor's fault.
Yep.
So, today we're going to kick off with particles, antiparticles, and photons.
Big fun.
Yay! A photon is basically a wave. We can start with a photon. A photon is a wave packet, is what people like to call it, which contains a certain amount of energy. The energy of a photon is proportional to the frequency of the wave. Examples of this is that UV causes skin cancer and X-rays can cause cancer as well.
Yep.
Basically, because it zaps you.
Yeah, basically it causes gene mutations in DNA, blah, 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 you get cancer.
Yeah.
Simple as.
Cancer.
Biology,
It's
really.
basically what I said wrong. Energy of photon, that's E, and it's measured in joules, obviously, is equal to Planck's constant, or H, or 6.63 times 10 to the minus 34, multiplied by the frequency, which is in hertz, as you might expect. If you want to know the wave speed, then obviously that's 3 times 10 to the 8.
Yep. Meters per second.
Meters per second, obviously.
In a vacuum,
which
blah, blah, blah.
Which equals the frequency multiplied by the wavelength. So if you ever need to find out the wavelength, you do the wave speed, which is most of the time, unless it's not an electromagnetic wave, then it's the 3 times 10 to the 8 divided by whatever the frequency is, or vice versa.
Also, wavelength, just so you know, there's a funny little symbol for it. Lambda, it looks like almost like a upside down Y.
Why doesn't it look like a lamb? Why isn't it like a cloud with a head and legs?
Because the Greeks were really annoying when it came to their letters.
I think the Greeks have very pretentious letters. You can look at the English language and look at our letters and tell a similarity between small case and uppercase. The Greeks,
Well, fair enough.
they named their letters.
What about D and D? You got little, got D, and then you got big D. Yeah.
Yeah, but you know where it's going.
No, you don't.
Whereas with some of these, it's a bit like sort of they started to draw an L and then they
Got bored.
died,
Yeah.
or something like that, or got shot,
By an arrow.
and it's just like, what is going on?
Okay.
Anyway,
We've
off topic.
Discovered
Connor.
that the Greeks' alphabet was rubbish.
Right,
Omega.
photons, wave speed. We've done that. You should know all of that by now. You've revised it. Pair production and annihilation. I
Right.
had a guinea pig called Toto Annihilation. I'm not even joking.
That's just freaky.
Go.
My grandma had a guinea pig called Fluffles, which got eaten by my dog.
Oh.
Well, her dog.
Anyway, pair
Right,
production and
you're going to get
annihilation.
your head around this. There's this thing called antimatter, which sounds scary, but it's not that hard. Antimatter
As in
is
matter, but
everywhere.
like all anti-inches.
No. Dear God. And you wonder why we keep taking so long. Anyway, antimatter is exactly the same as matter, apart from one crucial
But it's
detail.
not, though.
It's not.
It's the opposite,
I
though.
said no. It's got the exact same charge. Usually, no. Exact same
Oh.
mass. Christ.
Confusing them. Basically,
Let him
if you know them, basically the way to think about antimatter is a bit like Sam and Maddie. For Sam is anti-Maddie and Maddie is anti-Sam. But if you're not in with the inside joke, then an antiparticle can basically be produced by a high energy photon or the collision between other particles, which can be observed in the cloud change, if you must know. If a photon has a sufficient energy to create the rest mass of the two particles, so its energy must be at least twice the rest energy of each particle, then it can create pair production, which is creating a
Matter antimatter pair. Simple
Yeah.
as. Usually it's a positron and an electron because it's just the lowest energy one.
but it could also be a proton or an antiproton.
Yeah, could be anything really.
If a particle meets as antiparticle, they annihilate each other, producing two photons.
Which sort of shoot out in perpendicular, like. Pew!
A bit like you won't even go there. A bit like lightsabers, I think. You know when they hit and they go wow.
Yeah, well, they don't. Well, I don't know the physics behind lightsabers, but could be completely right.
What?
Probably.
It could be because two photons, they're light.
Yeah.
Two photons hitting each other, creating mass, which is why they rebound off each other. That might be. We have just the science behind lightsabers. The science behind photons have to be produced since energy and momentum would otherwise not be conserved, and that would be bad. Yeah, antimatter. If a particle and an antiparticle collide, then particles have antimatter counterparts called antiparticles. We've touched on that. They have the same mass, opposite charge, opposite values, baryon number, lepton number, ranges, etc., etc. Some examples: electron, positron, proton, antiproton, neutron, antineutron, and neutrino, and antineutrino. How imaginative. I always think they should call them Dave and Brian and Eugene.
No, they really shouldn't.
Eugene.
Remembering a name of antiparticles is really easy. Apart from the only thing you really have to know is electron, which goes to positron. So you kind of remember it is electron.
And you
has
probably
negative
would get
charge.
them up for putting anti-electron.
Yeah, you might. Probably would actually. But just think electron has a negative charge, so opposite of that's going to have a positive charge, positron. Simple as. Anything else is just the anti-particle.
Positron, positron.
Jellyfish. No.
In nuclear physics, we use electron volts. To convert an electron volt, all you do is times it by the charge of a proton, I believe.
Same
or an
with
electron.
electron.
Well,
Negative,
probably negative.
positive.
So, for example, so you times it by 1.6 times 10 to the minus 19. Equally, if you want to convert it back into electron volts, you divide the energy in joules by 1.6 times 10 to the minus 19. Particle interactions. Virtual photons, the first one. This is electromagnetic force / interaction, whatever you want to say. The exchange particle is a virtual photon.
Yep.
You can put photon and get the mark. The photon represents the exchange of momentum between these two particles. Basically, they repel. It's quite hard to show on an audio recording. But think lightsaber again, except they touch.
I'm going to think magnets.
This might be it.
If you bring sort of two magnets, both south poles together, to a certain distance, they will start repelling. It's the exact same thing, electromagnetism. When the two same charge particles, so in this diagram that we have and you can't see, which is really annoying, you've got a proton, and they sort of about on a collision course with each other, and when they get to a certain distance, they repel enough so that a virtual photon sort of travels between them, knocks them out of their path, and then they go off in different directions.
Yeah. And it's virtual because you can't actually detect them. So you don't
Yes.
really. Basically, they repel, and they decided that that's what happens in exchange of force. For the weak force, or the weak nuclear force, which I always put, but it's always weak force, or weak interaction, you have a boson, which is shown by W, and then the exchange particles, which are responsible for beta decay. Neutrinos can very weakly interacting, but they do interact in this force, in this interaction even. A boson must carry charge and mass. Mustn't it, Connor? Why?
I don't know.
To
It
have
just does.
continuity.
I don't know, to keep the-
Yeah, there we go.
Keep the conservation
Bosons
of
have
mass
a
and charge.
non-zero rest mass, short range, and are charged in comparison to photons, negatively or positively. For example, if you have a neutron going in, and a proton coming out, then you've magically got a positive. So if you like, you're offloading the negative. So it's kind of cancelling out. It's kind of maths, making it the same on each side, which makes a beta or electron even. Electron, beta, which one's preferable?
Beta minus is an electron, but I think beta is probably preferable just so the examiners don't get confused. Just put beta minus, please.
Poor little souls, yeah.
Get easily confused.
Yeah. W plus bosons decay protons into a positron and a neutrino. So you're going to go for neutron going to a proton. You use W minus boson, which makes an electron or a beta particle and an anti neutrino, which is continuity of lepton number, charge, etc., etc., etc. If a proton is turning into a neutron, it's the opposite. So you're having a positive W plus boson, if you like, which obviously makes your neutron, and then you've got a positron or a beta plus decay, and then you have a neutrino.
Not an anti, ordinary neutrino.
Ordinary neutrino. Then electron capture is the last one you really need to know about, which is under the heading of beta decay due to the weak interaction used in the boson, basically. A proton-rich nuclei can capture orbital electrons through the weak nuclear interaction. Here a boson changes the electron into a neutrino, basically. So you have a proton and an electron going in, then W plus.
You've got a neutron and a neutrino
Neutrino
coming out. Simple as.
So should there be an anti-neutrino? No, because it's
No.
going off,
Yeah.
so it's going to have the...
Right, we know what we're doing.
Right, anyway. Now, classification of particles.
Big fun.
Yay! Leptons. We'll start off with leptons. Leptons interact through the weak interaction. They're fundamental particles, meaning they cannot be divided into other particles. They have no internal structure. There are two charged electrons, the electron and the muon. Don't say anything. I know there's another one, but we will not go there. So each of the charged leptons have an associated neutrino. You just basically put whatever the symbol is for the electron or muon as a tiny little subscript. Subscript? Subscript. What's the bottom one? Subscript.
Sub.
Got it right. Each lepton has an antiparticle. Leptons have a lepton number of 1. Antileptons have a lepton number of -1. You don't know this. They have a strangeness of 0. You should also
What
know.
muons are, if you're kind of struggling to get your head around this, muons are just heavy electrons. They have the exact same charge but have much more mass.
Yeah. Muons are just American electrons.
That's
okay.
kind of harsh.
No.
But yes.
Yeah.
Yes. I'll concede that point. I have American relatives. I'm
We've
sure
just
they'll
lost a
listen to this.
demographic.
Oh God! Sorry, America. We love you, really.
I don't.
I don't.
Hadrons. Hadrons are a number of larger but not fundamental particles, different to leptons. Some are charged and some aren't. All hadrons except protons are unstable, which means that they will decay into a proton eventually. For example, a neutron will decay with an 11-minute half-life if it is free of the nucleus. Quarks and antiquarks. Basically, quarks experience a strong nuclear force and are constituent particles of hadrons. Therefore, they are fundamental particles. Baryons, it splits... Oh, for God's sake.
Baryons
can't
always
take
have
this.
3 quarks in them. So you do have different types of quarks, but we'll come on to that later. It's quarks, by the way. The Americans call it quarks. Anyway, baryons always have 3 quarks in them. Mesons, which are a different type of hadron, they're sort of little subsections. You've got baryons and mesons. Mesons are always a combination of a quark and an antiquark. Now, I'll come on to how to sort of rearrange those later. Properties of a particle is the sum of the properties of its constituent quarks. So if you have a proton, which has a positive 1 charge, the quarks inside it must have an overall positive 1 charge.
Yeah.
So you must have either 3 plus 1/3.
He basically just has to reach it.
Yeah,
and just touch on baryons and mesons. Mesons are basically hadrons that do not include protons in their decay products. And they're not baryons, so they have a baryon number of 0. Baryons have a baryon number of 1, as you'd expect, or -1 for antibaryons. Baryons are hadrons which decay into protons, basically. That's if you're doing it. And obviously, in all nuclear reactions, there must be a conservation of charge, momentum, baryon number, lepton number, and strangeness if it is the strong force. Otherwise,
If it's the weak
strangeness
force, it
doesn't
can
work.
vary by 2,
Yeah, it's
I
a bit
think.
awkward. Basically it doesn't. If they ask
Yeah.
you what is not conserved, then
In the weak
strangeness
force.
is probably your best bet. Strangeness was introduced following the strange tracks observed in the bubble chamber. You don't really need to know that, but there we are. Strangeness is always conserved in a strong interaction. Strangeness is not always conserved in a weak interaction. Strange particles decay through weak interaction. That's basically why. Inside a hadron, you have extra high energy electrons. Extra high energy electrons when fired at a hadron are scattered, which basically means there's something in it. For example, if I were to throw a high energy saucepan at Connor's head, it would probably explode, exposing. Well, actually, there might not be many particles inside them. Oh.
He's funny.
This shows that hadrons are not fundamental particles, but consist of point-like charges, if you like. Baryons have 3 and because they're quarks. There's one inside them. We're now going to read a row each of what quarks. Then you need to know up, down, and strange. Ready? Go up.
Up, they have a charge of plus 2/3 of a charge on the electron, of 1 on the atom. They have a baryon number of plus 1/3, and they have a strangeness of 0.
Down, charge minus 1/3, baryon number 1/3 or plus 1/3, and strangeness 0.
Strange have a charge of minus 1/3, they have a baryon number of plus 1/3, and a strangeness of -1.
So basically, it's strange, but it's not. But yeah, all you need to know is that a proton has up, up, down, and no strangeness, because there's no strange particle in there.
A neutron has up, down, down, which cancels out the charge, and it has strangeness of 0.
And then you can know pion, kaon,
Kaon.
kaon 0, kaon plus, sigma, or an antiproton. You can know any of them, but they're not really essential, so I'm not going to bother telling you. Except I will tell you antiproton is just anti. Instead of up, up, down, it's anti-up, anti-up, anti-down.
Yeah.
And same for neutron, it would be anti-up, anti-down, anti-down. And yeah, that's basically all you need to know. For the strong force, if we haven't touched on it, the strong force acts on hadrons and quarks. And it has a very short range and acts within the nucleus and is responsible to hold the nucleus together, with the exchange particle being the gluon. If you've seen a graph that looks a bit like it's got a really deep dip, then it goes up, it's got a little lump and it's flat, that's basically saying that it experiences a particle coming towards the nucleus, experiences very low force until it gets to a point where there's slight resistance, but once it gets over that resistance, it's basically in the dip that is in the graph, and it's really hard to get out because it's so strong, but it's really short range, which is all we need to know really for that. And that's it. Particle physics part 2 done in 16 minutes. Wow, that isn't bad.
Half an hour for the entire syllabus. I think that's all right. Well, for particle physics, not the entire.
You just
be quiet.
Okay,
yes.
Right. So, thank you for listening to another episode of Particle Physics with me, Will Carne.
And me, Conor Derkin.
Connor's eating chocolate from Austria.
It's lovely.
Don't even go there. Thank you for listening. Goodbye.
Bye-bye.